Hi everyone, Kevin here, back with more review questions for exam number 2. If you missed it, see the first video for questions 1 through 4. Let's pick up with question 5. This is a simple conversion question. We've been doing these all along. In this case, we have a bike tire with 45 psi. So our starting units are psi, pounds per square inch. Our ending units are going to be atmospheres. So we will need conversion factors that'll get us from psi to atmospheres. So let's look at our table 4.6. We have psi to torr, and we have atmosphere to torr, but we don't have psi directly to atmospheres. So we're going to have to go through two conversion factors. So the first one, I'm going to change this a little bit. Our first one is going to be psi going to torr, and then we will go from torr to atmosphere. And these are all units of pressure. So our conversion factor that we will use for psi to torr is 1 psi to 51.7 torr, or 51.7 torr to 1 psi. So which one are we going to use here? Well, our ending units are in torr, so we want to use the conversion factor with torr in the numerator. All right, so these are our two conversion factors here, and we're going to use the one that's 51.7 torr over 1 psi. So let's do the math on that. So we've got 45 psi times 51.7 torr per psi. So we've set this up correctly because psi will cancel in that first term, and in the numerator of the first term, essentially, especially if we specify that that's 45 psi over 1, which we can always do. That shows psi is in the numerator here in the first term. It's in the denominator in the second term. Those will cancel, and we'll do the math. The answer is 2,326.5 torr. Torr is the only units remaining that we haven't crossed out. That is going to be in our answer. Of course, I have to spell it right. So we're at 2,326.5 torr. I will not round that right now. I want to do the next conversion first, and that's going to be from torr to atmosphere. So in that case, we've got 1 atmosphere is 760 torr. And of course, we can write that in the opposite way as well, but I won't do that here because I know that we want to use the one that has 1 atmosphere in the numerator and torr in the denominator. So I'll set that up like this. Torr will cancel here and here. And if I do the math, I get 3.06 atmosphere. 3.06 atmospheres. And that will, let's see, we had 2 significant figures up here in 45 psi. So I would round that formally to 3.1 atmospheres to give us 2 significant figures, just like we had in the beginning. So that's how we do it. Very simple conversion. I do one more check, and that's to make sure that 3.1 atmospheres makes sense. Well, I know that that 14.7 pounds per square inch is 1 atmosphere. I just happen to know that. It's what we experience at sea level. 1 atmosphere of air pressure at sea level is about 14.7 psi, or around 15. So here, if I have 45 psi, that's, if I divide that by 15, I get 3, and that's about what my answer is. So looks like I'm good, and I'll move on to the next problem. We dropped 10 grams of potassium chloride in water. So the first part is, what is the equation for the dissolution of potassium chloride in water? And we looked at similar equations a couple of times in lecture. So we have KCl, and it's a solid, and when we put it in water, it is going to dissociate into potassium ion, and that's going to be aqueous in water, AQ, plus chloride ion, and that is also aqueous, dissolved in water. Now, the first question I would ask myself before writing this is KCl soluble in water? And we said that sodium salts and potassium salts are soluble in water. They're both soluble. So we have high confidence that, in fact, this does dissociate. The salt, KCl, does dissociate or come apart in water into 2 ions, potassium ion and chlorine ion. So I have confidence that this is the right equation. Then B, so that's A. In B, draw a picture of the solvation of KCl by water. So in water, we have potassium ion and chloride ion. Potassium has a positive charge, so we know that will attract the negative pole of water. So the oxygen in water will be oriented toward the potassium, right? Because oxygen has that partial negative charge, and the hydrogens have the partial positive charge, right? I can also add the lone pairs on oxygen here to make it a little more complete. And if I'm going to draw the rest of the solvation of water, I would draw a bunch of waters all the way around potassium, surrounding the potassium, in each case with the oxygen oriented toward the potassium, because the negative pole of water will be pointing toward potassium. The chlorine, on the other hand, will have the positive pole, the hydrogen, oriented toward it. So it will be surrounded like this with water molecules, with the positive pole oriented toward the chlorine. All right? And exactly how you draw the rest of the oxygen or the water molecule is not that important. The main thing is that you show that the positive pole, the hydrogen, is the one that's oriented toward the chlorine. All right, that's how you do this problem. Next. Here we're drawing hydrogen bonds between ethanol and water. And we did this in class. So this is just, it's a repeat, but for practice, I think it's a good one. So here is ethanol, CH3CH2OH. I'm going to draw the lone pairs. And let's just review the ethanol molecule. The hydrogen bond acceptors, I'm going to star with a blue star. So that will be this lone pair here and this lone pair here. Both of those can be hydrogen bond acceptors. Let's give this a purple star for the hydrogen bond donor. And that would be this hydrogen here. That would be a hydrogen bond donor. Note that the other hydrogens on ethanol are not hydrogen bond donors, because those hydrogens are bound to carbon, and that makes a neutral bond. right? We have to have a polar bond to be able to do hydrogen bonding. Okay, so we've identified our hydrogen bond acceptors and our hydrogen bond donor. Now we just draw in our waters. And so our water, one water would be here with the hydrogen oriented toward the oxygen of ethanol. And the hydrogen bond we would indicate with these parallel lines like I'm drawing now. And of course, we know that there could be another water oriented on the oriented to form a hydrogen bond with the other lone pair on that same oxygen. So those two look good. And then we can put another water molecule here. And you can draw in the lone pairs. And there would be a hydrogen bond between the hydrogen bond donor on ethanol, the purple star hydrogen, between that hydrogen and the oxygen, one of the lone pairs in the oxygen of water. So we end up with 1, 2, 3 potential hydrogen bonds between ethanol and water. And I say potential because hydrogen bonds are breaking and reforming all the time. But you could have 3 hydrogen bonds at any one point in time between waters and an ethanol molecule. Last question in this review guide, draw the Lewis structure of oxygen. Okay, so O2. So what do we do first when we're drawing a Lewis structure? First, let's determine the number of valence electrons. Or E minus, again, -1 charge on an electron, so we sometimes abbreviate it E minus. So in this case, we have 2 oxygens, right? And oxygen, how many valence electrons does oxygen have? And it has 6 each. So we have 12 valence electrons. So now we can start to distribute those around the 2 oxygens. So we have oxygen and oxygen. Let's put 1 pair of electrons around the oxygen. And then let's fill in lone pairs. So we have 1 lone pair, a second lone pair, a third lone pair. So now we've used up 8 electrons. We have 4 to go. So we could put another lone pair here and another lone pair here. And are we good? Let's count electrons around each atom. So I will circle the electrons around this oxygen on the right in blue, and we have 8. That's really nice, hunky-dory. We've satisfied the octet rule there, but the other oxygen on the left only has 6 electrons around it. So we are not done. So let's try again with 2 oxygens. And this time we're going to move one of these lone pairs between the 2 to make a double bond. And if we do that, we've used up 4 electrons. We've got 8 more to go. Let's put 2 electrons on each, or 2 lone pairs on each of the other 2 oxygens. And now when we count electrons, we've got 8 around the oxygen on the right, and we have 8 around the oxygen on the left. So the 4 electrons in the double bond are shared or are credited to each of the oxygens. So each of them effectively has 8 electrons around it and meets the octet rule. All right, thanks for watching. Let me know if you have questions. Good luck with the studying for the exam.